Hello, everybody. So we're going to start the introductory topic that I mentioned before, that we need to understand well before we go through the Moody diagram. So this is about plotting data and how we can plot data on different types of scales. So just to understand this, I will go through a simple example where we have data of x versus y, and x goes from 1 to 15, y has values from 447, and it increases up to 177,000. And let's say we want to plot this data on a regular graph. So when we plot the data, if we do plotting data the way we are used to, this is what we get. You'll see here that the x-axis scale is simple. There's nothing wrong with it. It's 0, 2, 4, 6, 8 until 16, so it's fine. But for y scale, we have it. We have to have a scale that will accommodate all the range. So the range is from 447 up to 177,000 or 178,000 almost. So the scale starts from 0, which is less than the minimum y, and to 200,000, which is more than the maximum y. So this is the range of y that we have. And you would see here that we have all the data plotted on the graph. But we need to revise an important point, which is what is the goal of plotting data. The main goal of plotting data is to present the numbers in a way that is easy to understand and easy to grasp. So it will be much easier to understand the trend of numbers and their increasing and how the relative value of different numbers on a graph than by looking at all these numbers on a table. But what you see here is that the goal is not achieved in a proper way by plotting the data like this. Since we increase the range of y-axis so much, the values here, the two maximum values, are easy to get the values of, but these small numbers are all not very clear. You see here that from 1 up to 10, which is like 66% of the numbers that we have, are all in this very small area. So you cannot tell clearly what is the difference between this y, the value of this point, this point, this point, this point. You can get it with kind of an estimation, but it's not a clear estimation. For instance, this number will appear to be 0 while it's 447. So this is all because the very, very wide range made the y-axis very, very wide, and so the step is very large, so it will include a lot of data in a very small place, which makes understanding the numbers not very possible using this way. So one thing that you might think of, okay, we can solve this problem by increasing or decreasing this step. Let's say make it 1000. So if you make this step 1000, then you have 447 would be clear from 0 to 100, 1000, from 1000 to 2000 you would see this, and so on. But still you will have a big problem here, that in order to accommodate all the data, including these two, the 100,000 step will need to keep going up to 200,000, which means that we will need a scale that is 10 times larger than this. So it will be like one story or 2-story buildings just to cover this, which is not logical and not possible. So and this is, by the way, this is one thing that we see a lot in our engineering applications, that we'll have data with a wide range of values or different orders of magnitude. So we have to see or find a way to present the data on the same graph in a proper way. So one solution is to calculate the log of all the numbers. So if you calculate the log of the numbers, the main function of the logarithmic function is to get the power. So when I say, for instance, log 447, it is 10 power 2.65, so the log is 2.65. So it's the power of 10 that will give this number. For instance, 1620, it's 10 power 3.21. So the log of this is 3.21, and so on. For instance, this is a clear example. It's almost 10,000, so it's 10 power 4. So the log is 4. So this is the main function of the main use of logarithmic function. So when you take a look of all these numbers, you'll notice here that the numbers are ranging, instead of being from 400 to 177,000, it's ranging now from 2 to 5. So it's making the range very, very narrow compared to the very, very wide range as before. So if we plot log y versus x instead of y versus x, you'd see here that we see all the numbers very, very clearly. So you can easily tell that this is log y is 2.65. So you know y is 10 power this number. For instance, for this number it is 3.7. Okay, so we get it very easily now compared to before. So one very, very common solution to this in these cases is to use log of the numbers instead of the numbers themselves, which makes the presentation of the numbers clear. And if you think of this, from 2 to 3 is actually from 100 to 1000, because this is 10, the actual y is 10 power 2 and this is 10 power 3. So this represents y from 100 to 1000, and this represents from 1000 to 10,000, and this represents from 10,000 to 100,000, and so on. So the range, the size available for the small range is the same as the size available for the large range. So we can see both in a clear way and in a proper way. Okay, so this is a good solution to this. However, this solution is not a very practical solution, because for this case you have to calculate the log of each one of the numbers, which is going to be a time-consuming process. You have to do this, and you have to have a calculator or a software to calculate all these logs, and from the logs you can put them on the graph. So it's not a very feasible option. So to solve this issue, there are graphs that we call have a scale that's called log scale. Log scale means that the scale that we have here is already a log scale. It's not a linear scale like this. So it has the numbers put as log of the numbers, not just the numbers. So it looks like this. So it goes from 100. So this is exactly the same as this. If you look at the numbers, they look exactly the same shape. So what we did is we don't calculate the log. The graph itself is a log scale. So you put it as 100,000, 10,000, 100,000, million, and so on. And you just put the number. And since these are all, this is log scale, you need to put the original number, not the log of the number. So for instance, here it's 447. So for this scale, it is 100, 200, 300, 400, 500, 600, 700, 800, 900, and then 1000. Then we go for 2000, 3000, 4000, 5000, 6, 7, 8, 9 until 10,000, and then 20, 30, 40, 50 until 100,000, and then so on until million. So instead of calculating the logs, the graph itself contains the numbers put as logs of the numbers. So it's not the actual number, they are log of the numbers. So when you put 447, it's here. So you don't need to calculate the log anymore. It's already putting the actual number on the log scale, means that it's the log of the number. Okay, for 2 we have 1600, so this is 1000, 2000, so it's going to be somewhere here. This is for 10 power 4, it's 8, so it's 9999, so it's 10 power 4, and so on. So this log scale is very, very, very useful, because it solves this issue. We don't need to do the calculations of the log anymore. You just put the numbers as they are, but you need to understand how this graph works. So this is a very, very, very useful type of graph, and we use it a lot in our, as I said, in our engineering applications. The scales that we deal with can be what we call semi-log scale or log-log scale. The semi-log scale is a scale where we have one axis is a log scale, like here in y-axis is a log scale, and the x-axis is a linear scale. Okay. So here you see, one thing you need to notice here is that as you go on the log scale from 1 to 2, larger than 2 to 3, larger than 3 to 4. So the distances between the numbers decreases as you go closer to the next 10. It's the power 1. So the step from 0 to 1 is bigger than 1 to 2, from bigger than 3 to 2 to 3, bigger than 3 to 4, and the smallest is from 9 to 10. Okay, so this is what we call semilog. It can be the opposite. It can be the x-axis is linear and y-axis is logarithmic, depending on which one of these two axes has values with very wide range. The other type of scale is what we call a log-log scale, and in the log-log scale, both axes are logarithmic scales. So you'd see here that this scale is from 1 to 10, from 10 power 0 to 10 power 1, with this uneven distances between the different ticks, and the same here for the y-axis. Again, this is if this is from 1 if this is from 1 to 10, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If it's from 100 to 1000, then 100, 200, 300, 400 until 1000, and so on. So this is how the log scale works. Again, it's a very, very common type of scales that we see. This is what we are using. This log scale is what we're using in the Moody diagram. So I prefer to discuss the log scale and how we understand it and how we deal with it before we go through the details of Moody diagram, to be easy for us to understand. So I'll stop here, and next time we'll continue, inshallah. See you.